Hopefully this probably starting soon. All right, cool. I think we started, or you just watched me stare blankly at the podium for the last 10 seconds. So first, we're going to take you behind the curtain. This is the third time I've tried to record this lecture. Third. One time I got run out of here by a class I didn't know was coming. One time the system was set up wrong, unbeknownst to me, and I wasted an hour and 15 minutes recording an unusable lecture. And now's the third time. So we're going to see how this goes. All right, now for the formal stuff. Now that you've seen, again, if I seem broken as a man, this is why. 3 times doing the same lecture in the same day. All right, so I'm recording this lecture so that you can watch it on your own. You're going to be responsible for this material come test time. We will do a brief review of it. The class after I tell you that you should go watch it, just to make sure everyone's on the same page. But this material is pretty easy and pretty straightforward. So I think that it is something that you can do on your own and really grasp. And then this is going to give me lecture time later in the semester when we do some stuff that's actually more difficult. All right? So we are going to first, there we go. We're going to talk about molecular properties. So we're going to talk about how atoms, bonds, and functional groups in a molecule will affect its properties, right? So if you have ethanol, right? Ethanol gets you drunk, but again, you guys don't do that because Wally the Wall Pond Carol says it's bad, right? But if you replace the oxygen in ethanol with sulfur, you get ethane thiol, which is the terrible smelling stuff they put in natural gas to make it smell bad. I would assume you wouldn't try to drink that, but you know, desperate times call for desperate measures, right? I break physical properties, or properties in general, into 2 broad categories. First, bulk properties, and these are properties reflected by a group of molecules. So that's mainly boiling point, melting point, and solubility. And then I have single molecule properties. So these are properties that are specific to one particular molecule in the group. And that is molecular shape, we'll talk a little bit about, and then conformation. So we're going to cover the bulk properties and molecular shape. Actually, molecular shape a little bit first. And then we're going to leave conformation and a lot of the other single molecule properties for class. All right? So the first thing we're going to talk about is chemical structures. So how atoms in a molecule impact different properties. So the first thing we're going to talk about is alkyl halides. Right? So the different alkyl halide, if you change an alkyl halide in a molecule, you get different properties. Right? The first thing we're going to talk about is kind of like bond strength and reactivity. So since I've given this lecture twice today, I have all my slides are already written up. I'm going to go through, I went through and erase some stuff, but just try to like pause things, and I'm going to, because there's going to be a lot of material that's already written and I'm not going to have to stop and write. So a lot of the examples are going to go by pretty quickly. All right, so we look at our alkyl halides, carbon fluorine, carbon chlorine, carbon bromine, carbon iodide bonds, right? So the carbon fluorine bond is the shortest of those bonds, when the carbon iodide bond is the longest of those bonds. Don't freak out. I don't expect you to ever remember numbers. I want you to remember trends. I want you to remember patterns. The numbers are here because I think they help to some degree, but don't get bogged down in the numbers and miss the bigger picture, right? So, carbon fluorine bonds are short. A short bond is a strong bond, right? So the carbon fluorine bond is short. It has the highest bond strength, 108 kilocalories per mole, right? The shorter the bond, the stronger the bond. The iodide bond is the longest bond of this group, right? it is the weakest bond of the group. It's basically half as strong as the carbon-fluorine bond. So what does this bond strength tell us? Well, a really strong bond is not reactive. Carbon-fluorine bonds are not very reactive. They're not good at doing any kind of chemical reactions. Carbon-iodide bonds are reactive. They're easy to break because they're weak. So the stronger your bond, the less reactive that bond is. Right? Now, I like to talk fast because I kind of want to go watch a movie because it's Friday night. And I have a teeny, tiny, eeny, weeny, pathetic bit of a life. So if I go a little fast, pause me, make sure you keep up. Right? So now, oxygens in molecules. So the oxygens of an alcohol or an ether have the same geometry as water. Right? So go back over here. Right? So if we look at water, the oxygen in water is sp3 hybridized. Right? It has two lone pairs. Two lone pairs. There you go. Has two lone pairs. And then two groups bonded to the oxygen. The geometry of water we call bent. Again, this should be a flashback to Gen Chem. You should be having twitching, and crying because it's Gen Chem. Right? If you look at an alcohol, again, the oxygen is sp3 hybridized. I've circled your two lone pairs here in blue, and you replace one of the hydrogens on water with a carbon chain. Doesn't matter what the carbon chain is, right? So it's basically the same thing as water, and again, the geometry that you get is bent. So around that oxygen, you're going to have a bent geometry. If I replace the hydrogen of the alcohol with a carbon, right? Now I have an ether. Again, my oxygen is sp3 hybridized. I've got two lone pairs, so again, my geometry around that oxygen is bent. Right? Nitrogens of the amines have the same geometry as ammonia. Right? So it's trigonal pyramid or trigonal pyramidal. Yeah. This is where I tell you that I can't spell. If I haven't said that in class, I spelled on a third grade level, and that's embarrassing to third graders. So just bear with me. Okay, they didn't hire me to teach English. Okay. So we have nitrogen. You've got three groups, right? And a lone pair, again circled in blue. The nitrogen here is sp3 hybridized, and its shape is trigonal pyramidal. But you can see I cheated and just triggered, and I can't spell. Right? So, doesn't matter if you have a primary, secondary, or tertiary amine, they're all going to be sp3 hybridized. They're all going to have a lone pair. So all of these nitrogens are going to have the same geometry as ammonia being trigonal pyramidal. All right, so we're going to talk about boiling point, right? Boiling point is the temperature which a compound changes from a liquid to a gas. And the more tightly the molecules are held together in the liquid, the higher the boiling point, right? So if all these molecules are really stuck together really tight, you're going to have a higher boiling point because it's going to be harder to pull them away and put them into the gas phase. If they're weakly held together, then it's easy to knock them out of the liquid and put them in the gas phase. Right? Oops, sorry, wrong one. Here we go. Nope, wrong one. There you go. All right. So alkanes, so just simple hydrocarbons, are held together as a liquid by van der Waals or London forces. Van der Waals and London forces are the same name or different names for the same thing, right? Van der Waals forces are the weakest of the intermolecular forces, right? And these forces result from how close you can put molecules together, right? The closer you can put molecules, the stronger these forces are. Right. So over here, I don't know what just happened. It frightens me. There we go. Right, so over here, you can see I've got these two pentanes close together, and then these little red lines I have in here, right? This guy here, this guy here. These are the van der Waals forces. So as you can put these molecules close together, you end up increasing the van der Waals interactions, right? So the longer the chain, the more van der Waals interactions you can have. Basically, there's more surface area for when these molecules get close together, so there's more attraction. So for every CH2 you add to a chain, you increase the boiling point by about 20 to 35 degrees. So pentane has a lower boiling point, so pentane has a lower boiling point than hexane because hexane is longer. It has an extra CH2, right? So whenever you add a CH2 in a chain, that is called a homologous series. So if you go 5 to 6, 6 to 7, 7 to 8, that is a homologous series. So, 8 carbons has a higher boiling point than 7. 7 has a higher boiling point than 6, right? So every time you add a CH2, your boiling point goes up. Because as you put the molecules closer together, there's more molecule there to interact with each other, so you increase the van der Waals forces. Now I've got to skip slide 5 and come back here in a second. So as you add branches to, as you add branches to your chain, you lower the boiling point. Right? So if we look at this guy here, right? Sorry. Right? I look at the longest chain here, longest chain here, longest chain here. Right? All of these have 5 carbons. All have 5 carbons. Right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. They all have 5 carbons. Okay, so they all have the same molecular weight, but this has 0 branches. This has 1 branch. This has 2 branches. Right? So just based on the number of branches, you would say that this has the highest boiling point, 1. This has the lowest boiling point, 3, with 1 branch being in the middle. Right, so this is how I kind of present this stuff on tests. I give you groups of molecules and ask you to arrange them in order from highest to lowest boiling point. All right, so why is it? Why is it that having more branches lowers your boiling point? So if we go back to, I like to think of tetras in this example, right? So a straight chain hydrocarbon, right, is the long stick in tetras, right? Super easy, they all fit together really nice, right? So they fit together really well. You get high van der Waals forces in between everything because they pack together really nicely. They just fit together great. Right? So you get higher van der Waals forces because they fit together so well, and then you get a higher boiling point. right? Things with irregular shapes, or with molecules with branches, have irregular shapes. So now they fit together poorly, right? It's like if you move, you would like to have all your boxes be the same size, because you can put them in the truck and they'll fit really nice. Or going back to Tetris, right? Tetris wouldn't be fun if it was all the stick, because you just like put it all down and you don't have to think, right? You get irregularly shaped things and you have to try to get them to fit together as best you can, but they don't always fit well. Same thing with molecules. If you've got irregular shapes, you can see I've got like one molecule's here, right? It doesn't fit perfectly with this molecule right here. This molecule doesn't fit real well. This guy's kind of like stuck off to the side. So they don't fit real well together, right? So you get poor fit, and then that leads to lower van der Waals interactions, and then a lower boiling point. So the better they fit together, the more they're able to like, I don't know, spoon, right? The better they spoon, the higher their van der Waals interactions, right? Poor spooning, low van der Waals interactions, right? Let's do some examples. You can pause this and then work through it and then take your best guess at it and then listen to my answer. All right, so I'm going to look at this. Here's my long chain, right? I have 2 branches. It actually says branches, I swear. I've got, 1 branch. And I have 0 branches. Right? I guess first I should have made sure they all have the same number of carbons. Got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. They all have the same number of carbons, same molecular weight. So now we're just going to basically order them by number of branches. Least number of branches, highest boiling point. Then I've got 1 branch, and then the most branches is 2, so this will be the lowest boiling point. Right? Have another one here. Right? How many carbons do I have? 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. All right, now figure out the number of branches. There's my chain, and my chain. All right. So I got 3 branches here off my main chain. I've got 0 branches, and I've got 2 branches. So just like before, same number of carbons, you just have to organize them by the number of branches. So this is going to be the highest boiling point, because it has the least branches. Second, and then this will be your lowest boiling point. Fair enough? Do one more. Again, pause it, work through it, then come back to me. Right, so this one, the one on top, you can just look at 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, I said 2, 3, 4, 5, 6, 7. So right now you just have to remember, as you go along the homologous series, the more carbons you have, the higher your boiling point. So, size does matter when it comes to boiling point, right? So this will be your highest boiling point because it has the most carbons. This will be your lowest because it has the least carbons. And then this will be in between because it has an in-between number of carbons. Now, if we look at the bottom one, each one has 1 branch, right? If the number of branches is the same, then you can just go off of how long the carbon chain is. Right? So this is 5 carbons, 6 carbons, and then 7 carbons. Right? So you can just go based on how long the chain is. So this will be your highest, middle, and then your lowest. Fair enough? So the longer the chain, the higher the boiling point. The more branches, the lower the boiling point. Pretty straightforward. So I'm going to surprise myself and see what's on the next slide. Right, I got to go back. Sorry, guys. And gals. There we go. So, we're going to talk about dipole-dipole interactions. So, when you put non-carbon groups in your molecule, dipole-dipole interactions become the driving force is the driving force that determines your I can't think, sorry guys. So, non-hydrocarbons are affected by dipole-dipole interactions. These dipole-dipole interactions have a greater impact on the boiling point than van der Waals forces. Right? Alright, so the van der Waals forces are still there, but they're comparatively weak. Right? So when you bond a carbon to a more electronegative element, you form a dipole. Right? So you might remember this. You have a positive end and then a negative end. So the arrow kind of points to where the electrons are. Right? So if Z is an electronegative element, nitrogen, oxygen, fluorine, chlorine, bromine, iodide, you're going to form a dipole where the carbon is going to be slightly positively charged and the Z group, whatever it is, will be slightly negatively charged. Right? And that forms your dipole. And again, R, I think we've probably going to talk about this, but R can be any carbon. So it doesn't really matter what's attached to your carbon. It just matters if it's got the Z group on it. So what that does, right, so I have a delta positive carbon and a delta negative Z group. And so the delta, the delta means slight. So I have a slight negative charge and a slight positive charge on my carbon. So what that does then is this positive and negative charge are attracted to one another. If you don't know this, opposites attract. Pull out Abdul video, check it out. It's got a dancing cat. Before dancing cats were cool. It's like a hipster dancing cat. Right? So, you've got this positively charged carbon wants to hang out by this negatively charged fluorine. This negatively charged fluorine wants to hang out by this positively charged carbon. So they act like little magnets that hold the molecules together more tightly than if they were just hydrocarbons. Right. So where do we go? Okay. All right, now we're going to talk about cyclic compounds. When a compound is cyclic, it has a higher boiling point than a straight chain molecule of the same number of carbons. So what do I mean? All right. Oh, again, flash ahead here. All right, so if you have pentane versus cyclopentane, a little first example here, pentane versus cyclopentane. Cyclopentane has a higher boiling point than pentane because cyclopentane is a ring. Same thing for really any other molecule. So ether versus a cyclic ether, right? They both have 4 carbons and 1 oxygen, right? But again, the one that is the ring has the higher boiling point, right? Now this is because if you are a straight chain hydrocarbon, right, we're going to talk about this a little later, you have conformations, meaning you can adopt different orientations in space, right? Sometimes you're going to hang out and be the straight rod, right? Sometimes you're going to kind of curl back up on yourself, right? And other times you kind of only half curl up on yourself, right? So these are all pentane, but it's pentane kind of in a different orientation. So if you can look down here in the corner, it's kind of like, you know, sometimes you're the Y, sometimes you're the M, sometimes you're the C, sometimes you're the A, right? You can be in a different shape, right? And you don't fit together real well, right? When you're the ring, you're always the O, like you're Ohio. You have a fixed shape. You don't have any other shape, so it's easy to stack you together. Right? So if we look at this, here's our cyclopentane, kind of drawn them on their sides, right? They all just fit together really nice. They just stack right on top of each other. There's no other way for this to kind of like flip around. It is just stuck, kind of sliding together. Right? Now, same thing with our cyclic ether. They just stack together as well. But in addition to having, you know, their van der Waals interactions, which is what's holding this together, right? So we've got our van der Waals forces here, holding these guys all together. Right, so those are all holding together van der Waals forces. Over here, you've got the van der Waals forces, like you would expect, but you also have all these dipole-dipole interactions, where the negative oxygen's hanging out by kind of the positive carbon by negative oxygen, so on and so forth. Right? So you have, oh, that arrow there. There we go. So you've got, they're able to fit together really nicely and get to their interactions. So because the rings can't like move around and they're kind of stuck, it's easier to fit them together. They fit together better, so then you end up with a higher boiling point. Right, now, I'm make sure I'm not ahead of myself here. Okay, so now you can mix and match now in these groups of problems, rings and straight chain molecules. Now, what I can tell you is, I don't know the difference in boiling point between hexane and cyclopentane, right? I don't know. But what you can do is look at a group of molecules and go, all right, this has 5 carbons, and it's in a ring. This is 4 carbons, and it's straight. And this is 4 carbons in a ring, right? So if you were to just compare 4 carbons in a ring and 5 carbons in a ring, which one has a higher boiling point? 5 carbons in a ring. If you were to compare 4 carbons in a ring to a straight chain with 4 carbons, what has a higher boiling point? 4 carbons in a ring. So with all that together, you can say, all right, I know this has a higher boiling point than this, and that this, and then this guy here has a higher boiling point than this. So from that information, I can say that this must be the highest boiling point. This is the second, and then this is my lowest boiling point. Right? Makes sense? Now on the next one, right, I got 7 carbons in a ring. And then 1, 2, 3, 4, 5, 6 carbons. And then 1, 2, 3, 4, 5, 6 carbons. Right? So now we know that 7 carbons is going to have a higher boiling point than 6. So this will be your highest boiling point. Right? Now, 6, no branch. 6 with a branch. 6 with no branch is second. And then the 1 branch is the lowest. Right? So you can basically know, all right, I know that this ring is going to be higher, and then let's just compare the other two. Where you can compare ring to ring, and then one of the rings to the straight chain. Figure out where everything fits together. They're not going to be real tricky. They're going to be kind of like this. You know, like I said, I don't know, I wouldn't know right offhand, oh, cyclohexane has a higher or lower boiling point than heptane. I can't compare those and get like a reasonable answer from first principles. So it'll be things that'll be easy to work through. Right, so here's another one. We got four choices now. He's going crazy. He's losing his mind. Oh my goodness. All right. So let's just work through this. I've got 7 carbons here. 7 carbons. 1, 2, 3, 2, 3, 4, 5, 6, 7. Got 7 carbons here. 1, 2, 3, 5, 6, 7. Got 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. So I've got 7 carbons on all counts. Right? What's going to have the highest boiling point? Well, the ring, of course. Right? So this is going to be the highest boiling point. Right? Now that one's out. Now it just comes down to, right, number of branches. So then this one's going to be second because it has the least branches. This one's third. This one's fourth and the lowest boiling point because it has the most branches. Right? So you just have to remember rings higher than straight chain. Straight chain higher than branched chains. Right. Now, as halides increase in size, the boiling point of the molecule increases. So the bigger the halogen, the bigger the boiling point. Right? So there's 2 reasons for this. Right? So we just start with fluoroethane and go down with all of them, chloroethane, bromoethane, iodoethane. Right? This has the lowest boiling point. So the lowest boiling point, and then this has the highest boiling point. Right? And why is that? It's partly because of surface area. Right? Fluorine is small. Right? Iodide is huge in comparison. Right? So if you have iodide, iodide is really big, so then there's more surface area for it to interact with other molecules to increase its van der Waals forces. Right? So it's really big, so it interacts with more molecules and you get greater van der Waals interactions. Fluorine is really small, so you don't get as many van der Waals interactions. Another way to think of it is I just kind of like to think about it as weight. Right? The heavier the molecule, the harder it is for it to go from being a liquid to being a gas. Right? It's harder for it to, for lack of a better term, jump out of the solution into the gas phase. Fluorine is a lot lighter than iodide, so it's easier for it to pop out of solution. Right. Another thing that affects boiling point is hydrogen bonding. So if you look at an alcohol and then compare it to an alkane or an ether with a similar weight, that alcohol has a way higher boiling point than you would expect. Okay? So for example, ethanol, I know the temperature ethanol boils at, I should. But ethanol boils at, let's say, 80. I'm not 100% sure on that. Don't hold me to that. If you have the ether, which is methoxymethane, methoxymethane boils at negative 140, I think. Right? It's still C2H6O, but it boils at like 200 degrees lower, if not more, than ethanol. And the reason for this huge difference in boiling point is hydrogen bonding. A hydrogen bond is a weak dipole-dipole interaction between a hydrogen bonded to an electronegative element, like oxygen, nitrogen, and fluorine, to another oxygen, nitrogen, and fluorine. Right? So this hydrogen right here, this hydrogen here, this hydrogen here, basically can go make a weak bond with another oxygen, nitrogen, and fluorine. Right? So you get something that kind of looks like this, where this hydrogen interacts with that oxygen and this hydrogen interacts with this one. So our blue bond here is our H bond. Right? Now, that hydrogen bond compared to the sigma bond between the oxygen and the hydrogen, that hydrogen bond is extremely weak in comparison. Right? But if you get enough of these bonds in the solution, or between multiple molecules, then that really starts to have a strong impact on the boiling point. Okay? So you have water, right? Oops, sorry. You have water. You can form a hydrogen bond between one oxygen, right? So you have a hydrogen bond there. Now the hydrogen bond is going to be from your hydrogen is slightly positive because it's bonded to an electronegative element, and that electronegative element is slightly negative. So what happens is this positive charge is attracted to the lone pair. So your hydrogen bond actually kind of goes to the lone pair on your other molecule. So it kind of is attracted to this lone pair, which makes sense because the lone pair is where the electrons are, and that's where your greatest amount of negative charge is located. So this hydrogen is positively charged or slightly positively charged because it's bonded to an electronegative element. It's looking for electrons. It's like, come on, where's some electrons? And it looks out, it sees another oxygen, and there's a lone pair there, and it's like, oh, dude, there's totally electrons there. I'm going for it. And it goes over there and makes a bond, and that's your hydrogen bond. Right? Now, you don't have to have a hydrogen bond between identical molecules, right? You can have a hydrogen bond between an oxygen of like ethanol and a hydrogen off of an amine, right? So again, here's our H bond, right? So we've got delta negative oxygen, delta positive hydrogen, delta negative nitrogen, delta positive hydrogen, right? And again, the negative elements are attracted to positive ones, right? Now everything I've shown you up until this point, you have an OH or an NH, and so the NH is donating its hydrogen and then accepting the hydrogen from something else. You don't have to be both a donor and acceptor. So in this last case here, I've got this NH. It's going to hydrogen bond going to be attracted to the lone pair of this carbonyl, and I get a hydrogen bond here, right? So the carbonyl has no hydrogen to give back to the nitrogen. That's fine, right? It's just you have to have an NH or an OH and then another oxygen, nitrogen, or fluorine for that hydrogen to interact with. All right, so things that are hydrogen bond donors. So things that can give a hydrogen to something else to make a hydrogen bond, right? That's any OH, so alcohol or carboxylic acid. Any NH, right? Primary, secondary amines. Primary, secondary amine, or primary, secondary amide, right? Or HF. Right? A hydrogen bond acceptor is any oxygen, nitrogen, or fluorine with an available lone pair. All right? So the oxygen of an alcohol, right? There are lone pairs there. This oxygen could be an acceptor, right? The oxygen of an ether, this could be an acceptor. The lone pairs or the oxygen of a carbonyl. So either if Z is an oxygen, it's an ester or a carboxylic acid. If it's a carbon, it's a ketone. If it's a nitrogen, it's an amide. Should I also put on here? If it's a hydrogen, it's an aldehyde. Right? As long as you have a carbonyl that has a lone pair, it can accept a hydrogen. Right? Amines. Right? Nitrogen has a lone pair. It can accept a hydrogen. It can accept a hydrogen bond. So, and then fluorine. Right? So, I can't write it in the corner because that's where I am. But so you have a fluorine. There you go. Right? One of those lone pairs can accept the hydrogen bond. So these are all examples of hydrogen bond acceptors. Oop. On to a new slide, guys. Hey, guys. Okay. So, talking about hydrogen bonding, and I know most of you are biology majors or are fish people. Not that you're like Aquaman or Aquagal or Aqualad, but that you're marine science people, right? You know, like hydrogen bonding, we're getting stoned. Why do I care? I'm going to be a doctor. I'm going to be a biologist. I'm going to swim with dolphins. Why do I care? All right, here's why you care. Biology people, fish people, doctor people. Here's why you care, right? Everything in your body, everything that's holding us together is pretty much hydrogen bonds, right? If you think about peptides, right? Peptides have 4 structures: primary, secondary, tertiary, and quaternary structure, right? Secondary, tertiary, and quaternary protein structure or peptide structure, all hydrogen bonding, right? Anti-parallel beta sheet, right? You have a hydrogen bond between an NH and a carbonyl of an amide. And that pattern repeats itself, and that holds 2 chains of amino acids together or in close proximity to give you a beta sheet in your protein structure. Beta turns, right? So when things loop back on themselves, they loop back on themselves in proteins because of beta turns. And a beta turn is you have the carbonyl of one residue is hydrogen bonded to the nitrogen of another residue that's 2 amino acids away. DNA, right? The building blocks of life, our genetic makeup. What makes me so dashingly good looking? Don't laugh that hard. It's just not cool, right? I'm not there, but still, I feel, right? So, what holds together are strands of DNA, or double helix of DNA. Hydrogen bonding is what holds together DNA. How do we break down proteins in our body? Half the time, or no, really all the time, it's hydrogen bonding weakening the amide bond so that we can break it down, right? So that our body can do something with it, right? So hydrogen bonding is really what is the glue that holds us together. And one hydrogen bond is really weak, but 1,000 hydrogen bonds is really strong, right? So hydrogen bonding is really important. All right, melting point. Melting point is the temperature where a solid turns into a liquid. Melting point follows a lot of the same patterns as boiling point, right? So melting point typically increases in a homologous series as molecular weight increases, right? So I know why that's there. I know why that's there. This more, oh, I'm sorry. I totally got ahead of myself. More examples, real quick. Sorry. All right. Totally lost my choo-choo. Right? So, big night to hydrogen bonding. We'll do the intro for melting point here in a second. Right? Hydrogen bonding. More hydrogen bonds, higher boiling point. Right? No H bond. Right, so you're just thinking, if I have a solution of this, is there any hydrogen bond? No. I've got one H bond donor here, donor acceptor, one H bond possible, two H bonds here and here. Right? So, based on that, I would say highest boiling point, then second, and then this would be the lowest boiling point because it has no hydrogen bonds. Right? Next up, same deal. Right? Here's one H bond. Right? Now this guy, these two, neither one can hydrogen bond. How are we going to tell those apart? Well, with the oxygen here, I can get a dipole-dipole interaction. Right? I get a dipole-dipole interaction. That's going to help hold those molecules together. So again, you're going to have one, this is the highest boiling point, then two because of the dipole-dipole interactions, and then three, this is going to be the lowest. All right. Sorry about the whole getting the melting point beforehand. But again, melting point increases in a homologous series. All right? So 4 carbons, 5 carbons, 6. Low MP to high MP. All right? Similar to boiling point, the more branches you have, the lower your melting point, for pretty much the same reason, right? So the better things pack in the crystal lattice, right? Better things pack together in the crystal lattice, the stronger that solid is and the harder it is to melt it and break it into liquid, right? So the tighter the fit, the higher the melting point, right? So as you put branches, as you put branches on your molecules, they don't fit together as well. Same basic premise as with the boiling point, right? Now, there's this little anomaly of life here, that alkanes with even numbers of carbons pack together better than those with odd numbers of carbons. So what this results in is that you have that even number carbons have even number carbon chains have higher melting points than odd number carbon chains, right? So there's a cool graph that you've kind of already got a sneak peek of, right? So evens are in red here, blues or odds are in blue, right? Let me fix my little gap here, right? So basically, your x-axis is your number of carbons, your y-axis is your melting point, right? So as you can see here, 4 to 5, 6 to 7, 8 to 9, 9 to 10, right? It's kind of like you're taking steps, right? I don't know the melting points offhand. This is just a rough guess, or not guess, a rough representation, right? So you go from 4 to 5, then there's not a big change in melting point. But when you go from 5 to 6, there's a bigger change. 6 to 7, there's not a big change. 7 to 8, there is a big change. Right? So if I were to give you these on the exam, I would try to either give you all evens or all odds. Right? That way you can just kind of stay on one path. Right? But in general, as you go up the homologous chain, there is you increase your melting point. So even 4 to 5, you're going to increase your melting point a little bit. Right? But you just have a bigger jump 5 to 6. 6 to 7, you're going to have a little increase in your melting point, but not as big as from 7 to 8. Okay? So they have two parallel curves that are just offset. So the evens in general have a higher melting point than the odds. But they both follow the same shaped curve. Right? Solubility. Solubility is a measure of how well a compound dissolves in a particular solvent. Right? So, when you were in Gen Chem and we talked about solubility, right? We talked about things going into solution and dissolving. That is the exact same thing that we're talking about here. The difference here is that in Gen Chem, you dealt with a lot of salts, right? And what do salts do? Salts in water dissociate, right? Sodium chloride, when you put it in water, breaks into sodium plus ions and chlorine minus ions, right? You wrote this out, you put the little AQ to show that it was in aqueous solution, right? Awesome sauce. Organic molecules aren't held together by ionic bonds. They're held together by covalent bonds. That means that you can't break, that organic molecules don't dissociate. Right? Organic molecules undergo a process called solvation. For an organic molecule to dissolve in any solvent, that organic molecule has to be surrounded by the solvent. It has to be enveloped by the solvent and just kind of move through the solution surrounded by a bunch of solvent molecules. Right? So, what has to happen is you have your water. So we're basically talking about water solubility. Right? You have your water, right? And it has to, right? Let me erase that. Right? So instead of breaking apart your molecule, you've got to put water molecules around your molecule, and you have to just enclose it in solvent. So now your molecule is wrapped in water. This is solvation. Right? Solvation is when your molecule gets wrapped in the solvent. Right? In this case, water. Right? Now, if you remember no rhyme, no little mnemonic device from Gen Chem, you should have remembered likes like likes. Right? Likes like likes. What does that mean? Polar compounds like to be dissolved in polar solvents. Non-polar compounds like to be dissolved in non-polar compounds, or non-polar solvents. So, as a result of this, non-polar compounds like hydrocarbons don't dissolve in polar solvents like water. Right? This is why oil and water don't mix. This is why you have to shake, you have to shake Italian dressing before you use it, because the oil and the water separate and they don't mix. Right? So, you can't dissolve pentane in water. Right? But as you add polar functional groups, like alcohols and amines, you will increase your water solubility. All right. So, oops. So if you look at pentanol versus hexane, right? Pentanol is going to be more water soluble. I promise that word is soluble. There we go. More water soluble than hexane because it has a polar functional group. Right? That polar functional group allows the water molecules to interact with that molecule and thus solvate. Right? So what are examples of polar functional groups? Well, alcohols, amines, carbonyls, like, so any carbonyl, ketone, ester, carboxylic acid, amine, aldehyde, or ethers as well. Okay. Now, the more polar functional groups you have, the more water soluble your molecule will be. Okay? It doesn't mean that your molecule is going to 100% mix with water, but the more polar functional groups you have, the more water soluble you're going to be. All right. So look at this. Oops, I apparently forgot to erase everything on this. That's all right. So I've got 3 polar functional groups here. 1, 2, 3. Right? I've got 2 polar functional groups here. I've got 1 polar functional group here. So comparing these, the one with 3 polar functional groups is going to be the most water soluble. Then the one with 2 polar functional groups is second, and then the one with only 1 polar functional group is third. All right? So there is a difference to how much a functional group contributes to water solubility, but we don't care. All of this is what you need to do is count. And say I got 3 polar functional groups, I've got 2 polar functional groups, I've got 1. All right, now I can arrange these in how water soluble they are. Okay? So why does the number of polar functional groups impact the water solubility? And that's because when you have a polar functional group, it gives the water something to interact with. Right? So if you have a hydrocarbon, right? Hydrocarbon here, I'll give you one. Right? You got a hydrocarbon. Right? There's nothing for the water to interact with, right? The water wants a hydrogen bond, it wants to interact with a dipole. There's nothing. There is nothing for the water to interact with. So the water's like, it's not you, it's me. I just don't feel anything. I just don't want to hang. Right? Right, so then you give it a polar functional group. Oh, you give it a carbonyl. Right? Now, great, look. Now I can hydrogen bond. Right? I can bring some waters over, they can hydrogen bond. I start to get some guys around. I can start to solvate this molecule. Great. Now, if I have 2 polar functional groups, you can have waters interacting with your carbonyl, right? And then you can have waters interacting with your alcohol, right? So the more functional groups you have, the more water molecules you can accommodate, right? This is why you have furniture. Work with me here, right? If you don't have any furniture, no one's going to come hang out at your house. It's just not going to happen. I do. I got a big TV. You can watch the game. But what am I going to sit on? Nothing. I'll go watch the game somewhere else, right? Now, sweet. You get yourself a couch. People will come over. They'll hang because they have a place to sit, right? You get a couch. You can have 3 people over, right? So you have one polar functional group, you can get some water molecules around, right? Polar functional groups are like, come on down, water, chill out, hey, right? Now, you got yourself a couch and a love seat at your house. You can bring like 8 people over. You can pile them in, have some fun, right? Right? Polar functional groups is like polar functional groups give water molecules a place to sit on the molecule. The more places you have to sit, the more water molecules come over. The more water molecules that come over, the easier it is for them to solvate your molecule. All right? So just remember, more polar functional groups, more places to put water, easier for the water to dissolve. I mean, for the compound to dissolve in water. All right? Did I miss anything? No. And boom. So take that, Khan Academy. That just happened. Raising the roof. All right. So watch this. Good job. We'll give a little review when we come back to class. But just make sure everyone's on the same page. I'll do a couple more examples, answer any questions, and then we're going to move on to confirmations or finish confirmation up depending on how the lectures go. All right. So thank you for sitting through. And now I'm going to stop this, and maybe you'll get to watch me dance when it doesn't stop. And stop.